All right, it's time for application day 2 here. We did area with our polynomials last time. It seems fitting to do volume now, right? We don't want to leave volume out of the equation. Equation. Okay, so let's see here. We have a manufacturer cuts squares from the corners of a 12 centimeter by 36 centimeter piece of sheet metal and then folds the metal up to make an open top box. You've seen this maybe with cardboard before, like if you get like a gift box, something like that. You can see how they fold up and whatever. It's kind of the same idea. So what we want to do is we want to write an equation to model the v of x, where x represents the height of the box and v of x represents the volume. Okay, so we'll want to jot that down. I think you know what might help? A three-dimensional picture. I'm going to draw one up real quick. All right, so got this box here, and when we're saying the height of x, I'll change color so it's not all orange. We'll go bears. So we got an x here. All right, and we're talking about when we're folding it up, so that would be these guys. All these would be x's, okay? I don't have to label all of them, but you know what? I'm going to label all of them because I just did. I just labeled everything. All right, so now it says that this part is 36 centimeters, and this is 12 centimeters. And, you know, if you can't do the fancy teacher brackets yet, just keep working, okay? You'll get there, I promise. All right, so what does that really mean then? Well, that means that this dimension here is going to be 36, but we're going to subtract an x and an x, so this would be 36 minus 2x. And the same idea can be applied. I'm going to run out of room over there, so I'm going to put it here. I'm going to do 12 minus 2x for that dimension, right? Because I'm subtracting x and x when I fold it up, okay? So this dimension, I'll label this one as my 36 minus 2x, and this will be my 12 minus 2x. So when we're doing volume of something, volume of a prism, a rectangular prism in this case, it's length times width times height, right? It's volume of a rectangular prism, and that's what we have. So if I want to write this as a function of x, right? Volume is a function of x. Well, it'll be my length times my width times my height. So we would have a length, we'll say, is our 36 minus 2x. I'd have my width is 12 minus 2x. And then my height would be x, and I left a space here for this reason. Even though the h is at the end, I think it looks better with the x out in the front. Okay, so there's my volume function. Now, I can figure things out with this volume function. That's why I wrote it, so I can figure some things out, right? So what size should he cut the corners to maximize the volume, and what is that max volume, right? So where should he cut these things so we get a nice volume of a box, right? We want the biggest volume possible. I think if we pull out a calculator and graph it, we could have some luck with that. I'm gonna pause while I type it in. Alrighty, so I've got this in my calculator here. I like to usually hit zoom 6, just zoom standard, see what it looks like in my standard window, see if I got anything that's helpful at all, or if I can eyeball it from here. With this particular one, yeah, this isn't going to be too great. Maybe why don't we try zoom fit? So zoom 0. Let's see what the calculator gives us. Sometimes it gives us something really easy to work with. All right, we got a lot going on below the x-axis, and when you think about a logical domain and range for this, the range, our function values should all be positive if we're talking volume. So this area right here is really not helpful to us, but I can see where that max is happening. Now, you could analyze it from here, but I'm going to change my window a little bit to just look a little better. I'm going to go with like negative, this is a huge 17,000. I'm going to go with like negative 200. Okay, not that big. All right. And then for this one, I'm going to go a little larger. I'm going to go like 700. Okay. And then I think my x's were fine, so I'll go ahead and graph this. So it's a bit of a educated guessing game, right? Boom. I like that. Now this is a cubic function. You can tell that it's not really symmetric right here like a quadratic would be, and that's right. I mean, this is 1, 2, 3 x's, so it's cubic. But I have my max here, and that's really what I want to find, right? So I'm going to hit second calc, and 4 is my maximum. Okay, so I'm going to get my left bound, my right bound. Here we go. It's a little slow moving, but that's all right. And boom, I've got 2.708 for my x, so 2.71. And then over here I have 545.296, so 0.3 then. All right, let's see if I can remember this because it's going to disappear. Lovely. All right. We can do 3.0 if we'd like to show that we were doing 2 decimal places for each. So, lovely. Well, what does this mean? Well, the x value is, in fact, my height of this box, isn't it? So, how should he cut the corners? Well, it's x by x for cutting the corners. So, 2.71 centimeters by 2.71 centimeters. All right, that's the first part. Second part, what is the max volume? Well, that would be my function value, right? My v of x, which is my y value, where that max was, right? So the height of that function, the max value, is going to be 545.30 centimeters cubed. And I've got both answers to the question. Lovely. So it's not just about writing that equation, writing that function, but also knowing what the heck that stuff means. I could ask, what are the dimensions of this box? And you would need to plug in the x here and here to get my 3 dimensions of the box. You can actually do that and multiply everything together, and you will get this answer. Okay. Granted, we did round here, so it might be a little bit different, but you would still get something very close to this answer when you did that. Okay. I think that's a pretty cool use of these things. People, they use this all the time in business to optimize things, to optimize how you're going to fit stuff into shipping containers and whatever. The shape of packaging isn't just like, hey man, this looks cool. Like, no, they analyze all sorts of aspects of it from a marketing standpoint, but also a shipping standpoint and size and all that. So very much useful in the real world, but this is obviously a little bit scaled down, right? It's a little more complex in the fancy business world. All right, let's move on. You know, actually, before we move on, there was something I wanted to touch on. Domain. You know, it's not asked in the question, but I think that talking about your domain of a function is especially important in these application problems. So what would be a logical domain given this application? Well, what's the minimum that this dimension could be? It's got to be bigger than 0, right? So I could go from 0 to, and what's the largest that it could be? Well, we could bring that graph back up and find out where it crosses the x-axis. And if I look here, it looks like it's crossing at 1, 2, 3, 4, 5, 6. Now, does that make sense? Well, actually, yeah, because if I plugged 6 in here, I'd get 0. We don't want our volume to be 0, right? So I've got to be less than 6. So I will go from 0 to 6, not including it. So that'd be our logical domain here, because we could ask you a question like that. What would be a logical domain given this application problem, right? It's not the normal domain of the cubic function. It's given the context, right? So that was just one more thing I wanted to touch on that I kind of forgot to mention because it wasn't part of the problem. Lovely. Now we can move on. All right, we're going to do a few little exercises here dealing with our application problems, and then we'll actually apply it. So we have if V is equal to h squared L, so some volume formula, and the length L equals 3 times the height, find the volume as a function of the height. So this is not only important in this class, but also very, very important in your AP Calculus classes. All right, so I want to write my volume as a function of height, meaning I shouldn't have L in there, okay? So I have this second function here where it's L equals 3h, and I want to make sure that it is solved for L so that I can plug it in to this function. Well, this one is already solved for L, so I can just go ahead and substitute all V of h then equals h squared times, and I'm going to substitute in the 3h, and then I'm going to simplify. So I'd have 3h cubed. We get V of h. So that one wasn't too bad because it was already solved for the L there, right? Wonderful. Excellent. Let's keep it going here. So the next one here, if A equals pi RL plus, there we go, plus pi r squared, and L is equal to 2r, length is equal to, or whatever dimension that is 2 times r, probably the radius. Find the area as a function of the radius, A as r, or A of r. All right. So let's think about this for a sec. So I have A of r, and since it says A of r here, that means we want to remove the L, right? We want it only, so we want to remove the L because we want it as a function of r. So when I'm writing this, I'm going to go like this. Pi r, and then I'm going to put something in place of L plus pi r squared. Okay. So now, well, I have this other function, L equals 2r. Well, this one, once again, is actually already solved for what we wanted. So I can just go ahead and substitute that in. Get 2r. All right. So now we can simplify. So if a of r is equal to pi times, this would be 2r squared. So maybe we'll do 2 pi r squared. I think that looks nice. And then plus pi r squared. And I wish I gave myself a little bit more room. So I'm going to put my final answer over here. A of r is equal to, well, all those together, those are like terms, aren't they? 3 pi r squared. And there's my final answer. I like it. Wonderful. Fantastic. Woo. Good stuff. Good stuff. All right. This last one here is a little bit different for number 4. So I've got, and we've got one more problem after that. I've got same setup, but this time we want a of L. Well, that means remove, rather than get rid of, remove r. Okay, so we only want L in our final function. So I'd have a of L is equal to pi, replace the r, L, plus pi, replace the r, squared. Okay. So let's see here. Over on the side here, I'm going to take this L equals 2r that we've been dealing with. But now I want to solve for r so that I can replace the r, right? So I'll divide by 2. And I'll get r is equal to L over 2. And I can take this right here and I can substitute it in to that part of the, or those two parts of that new function. So now I have all L's here, but let's go ahead and do some simplifications. So if a of L is equal to, well, this would be L squared, and that over 2, so we could say 1/2 pi L squared, and then plus, and this would be, well, if we're squaring that, that's going to be 1/4 pi L squared. And we can leave it like that. We could actually combine these because they are like terms. I missed a parenthesis there. My apologies. I could go with this. I'm like, why do I keep almost forgetting parentheses here? I think it's the curviness of the L there that I'm like, I already made a curve. All right. 1/2 and 1/4 would add up together to be 3/4 pi L squared. And I'm going to leave it like that. That's the most simplified, condensed, beautiful looking function that we have there. Area as a function of L, our length. I like it. Wonderful. Okay. Uno más. All right, last one here. So we have, suppose a cylinder is to be formed by rolling a rectangular piece of material. So like a soup can, or like if you think of like a soup label, right, how it wraps around there, it's a rectangle that wraps around to form that cylinder. The cylinder is to have a height which is 3 times the radius. So my height is equal to 3 times the radius. I'm going to jot that down. Write a function expressing the volume of the cylinder as a function of the radius and also as a function of the height. So V of R and V of H. So the volume of a cylinder is given by, it got cut off. But luckily, I also teach geometry. And I remember my volume is equal to pi R squared H. Boom. I like it. Awesome. Fantastic. We find the area of that circular base and we multiply it by the height. That's how we get the volume of a cylinder. Good stuff. Good stuff. I love using these kind of formulas. All right. So if I'm going to do the volume, let's start with this one. I'll do this in a different color. Let's go with the blue here. V of R. We'll do that one first. All right. So if I want the volume as a function of the radius, that means, and that means I only want R left over, right? So R squared, and then I'm going to leave a set of parentheses here. Now let's take our height equals 3R. Well, that's actually already solved for H, so I can just substitute that right in. 3R. So I'm left with pi R cubed, and actually I'm going to throw the 3 pi R cubed. Really, you can have these in any order because it's multiplication, but I think that probably looks best. So that's our volume as a function of the radius. Awesome. Fantastic. Switch colors again. I'm going to go with orange. All right. Now we want volume as a function of the height. So if I want volume as a function of the height, we'd have pi r. Nope, we don't want r. We want to take that out. Squared h. So if my function that I do know that height is going to be 3 times the radius, and that was a trickier part in this particular question where we gave it to you in the other 2 or 3 problems that we did, but now you have to actually take it out of there from words and create your own equation, right? So now I need to solve for r, so I'm going to divide by 3, and I'm going to get r equals the height divided by 3. So I can throw that in here, and now I'm going to have to simplify. So let's do that. I'm going to have h squared and 3 squared, that's 9, so that'd be 1 over 9 pi h squared and h. I'll slow down some of the simplifications here, but I'd have 1 over 9 pi h cubed. That's my volume as a function of the height. I like it. There's my final. It's beautiful. Did both. I forgot to circle the previous one, man. Oh, geez. I really should have circled that, but now it's not letting me get my color back. There it is. Boom. Awesome. Well, I hope you guys enjoyed these problems. Again, this skill of taking 2 separate ones and getting into terms of one variable is so very important, not only in this class, but in calculus. By getting into terms of one variable, we're able to use our graphing calculators to then analyze the function. You can't use 2 variables in there. It doesn't have that capability, right? So this way we can actually analyze it with one variable, and then we can use that to find the other pieces out as well. But this is a very useful skill, not only in this class, future math class, and you know what? I think real life too. All right, because volume and area are everywhere. You guys have a fantastic day. America, freedom, rock and roll, Costco. Stay hydrated and live the Raider way.